Similarly to what we did with subtopic 10.1 on describing fields, we're going to go back now and translate all of those understandings from electric fields across to gravitational fields. And the reason we can do that is that those ideas are easily transferable between the different types of fields. So those field concepts, when we're talking fields, we're really not, we can keep things fairly generic and not really specifically talk about the type of field if we really want to, but obviously it makes more sense to talk specifically about the type of field that we're interested in. But in this case we're going to look at gravitational fields and how they are similar but different to electric fields. And the way that we're going to do that, rather than go through and explain all of these concepts in a similar way to what we did with electric fields, we're just going to go through and look at the equations basically, because the ideas are very similar across the two. It's just about identifying the slight differences. So a bit of a table of sorts here, where we'll look at the particular quantity and then we'll specify what that means for both gravitational and electric fields. Now the first one, if we look at force for electric fields, we know that it's about Coulomb's law, and so the equation that we have there, we'll use the subscript E along the way here to identify when we're talking about electric fields. So for Coulomb's law, as we've seen, F is equal to kq on r squared. For gravitational fields, we have to refer to Newton's law of gravity, and the gravitational attraction between two masses is given by g mm on r squared. So we've seen both of those before, nothing new. They then lead into a few other equations that are useful. So the next one that we'll look at is potential energy. So we saw that for potential energy in electric fields, that electric potential energy is given by kqq on r. And again, if you want to go back and have a look at the derivation of that, you'll need to refer to an early video. For electric field, gravitational fields, in a similar manner, it's now gmm on r. So that's looking at the gravitational potential between two masses. So, and notice here we're dealing with a large scale, so we're sort of, say, looking at the moon and the earth, or the sun and the earth. We wouldn't generally look at, say, a car and the earth. We'd look at gravitational potential energy in a slightly different way, as we've seen in Unit 2. Now, if we then go to the next idea being potential at a point in the field, in this case, similarly sort of stepping along again, for an electric potential, it's given by kq on r, so that's the amount of energy per coulomb to move from infinity to the distance r away from charge q. For gravitational potential, we now need to look at it as being negative gm on r. Now the reason why it's negative here, if you think about this scenario of looking at the potential around a charge, we developed that idea based on field lines representing what happens to a small positive test charge. So that was for a positive potential, we'd have a 0 volts out here, and then we'd move closer and the potential would increase. For masses, we don't have a negative mass, we only have positive mass, and so we'll always have field lines going in towards. So in order to figure out the potential there, we basically have to compare it to, not to a positive test charge or positive charge over here for Q. That would need to be a negative charge, which means the field lines all point in the opposite direction. That can be accounted for in this equation because Q can be negative. In the equation for gravitational fields, mass can't be negative, so we need to introduce the negative term out the front there, hence negative gm on r. Finally, if we then look at field strength, so for electric field strength, as we saw, it's given by, it's a note here, it's a vector quantity, and that's given as negative delta VE on delta R. For gravitational field strength, we use the symbol G, so we're aware of that quantity already, and that's given by the negative change in potential, gravitational potential over the change in distance. And again, that's because the field lines for a gravitational field resemble the field lines for a negative charge, so we've got that comparison there again. The last one that we want to look at is the field inside a sphere. We'll do this graphically here, and a slight change between these two scenarios. So we saw that if we're dealing with a charged sphere, so if we're looking at a charged sphere, we saw that the relationship, so if we've got the electric field strength on the vertical axis, and across the horizontal axis we've got the distance r, that means that we have, say, points here and here that represent the radius of the sphere or the edge of the sphere. We saw that outside that the electric field is governed by the equation for electric field strength that we just saw previously. We then have an asymptote here and an asymptote here. So outside the charge, outside the sphere, sorry, we have those two lines, but inside the sphere the electric field was zero because the charges were evenly distributed across the surface of the object. Now if we look at a sphere with mass, so if you imagine, say, the Earth, treating it as though it's a large sphere, it's a different scenario. Because the Earth doesn't have all of its mass concentrated around the edge of the sphere, the way that charge is concentrated around the edge of the sphere, we have a different representation that we need to be aware of. Again, we can consider these 2 points being the radius of the Earth, or the radius of whatever the sphere is that we're dealing with. So again, we'd see outside the sphere that we're going to follow that relationship as given by gravitational field strength above. But now, as we move inside the sphere, so imagine sort of a giant tunnel down into the middle of the Earth. As you move into the sphere, you don't have all of the mass now concentrated above you the way that you would with a charged sphere. So the mass is actually now going to be evenly distributed throughout the whole substance. And as a result, it means that the mass that's above you is going to start to cancel out the effect of the mass that's below you. Now, if you want to get a more insight into this idea, you can have a look in the textbook, but basically all you need to really be aware of is that when you get to the middle of the sphere, because all of the mass is now going to be evenly distributed above you, the gravitational field strength there will be zero, but it will increase in a linear fashion as you move further out from the middle of the sphere. So we can see that there's a difference between those two. Excuse the messy lines on this diagram. They should be straight lines coming down into the middle of the sphere there. So there's some of the basics of the quantities that are similar between electric fields and gravitational fields, and you can see that most of the equations there are somewhat interchangeable, except that we're using quantities related to mass, so m and capital M and lowercase m for the two masses, whereas it was capital Q and lowercase q for the charges. The only other difference there as well that I forgot to mention, the value of capital G, we've already seen that in Unit 6, is the universal gravitational constant, whereas K over here is known as Coulomb's constant. So for Coulomb's constant related to electric fields, and the universal gravitational constant is related to gravitational fields. We'll have a look at a few of those sorts of scenarios in class and how we can use those equations for looking at, say, objects that are orbiting Earth or around the Earth in some way, shape or form.